So we have at this point seen a number of different estimators: the periodogram, the modified periodogram, Bartlett's method, Welch method, and the Blackman-Tukey method. So a natural question is, which of these estimators is the best? Which one should I choose in a particular situation? Now, this question doesn't have a unique answer because every different estimator has different properties which could make it suitable in a particular situation. So in order to pick an estimator that is suitable for what you want to estimate, you have to know about the properties of those estimators. Beginning with the periodogram, we know that the periodogram can be obtained by taking the discrete Fourier transform of our data sequence, taking its absolute value squared and normalizing by the number of samples. This creates a spectrum estimate which is biased, where the expected value of the spectrum estimate is given by the true spectral estimate convolved with the Fourier transform's absolute value squared of the window, where the window in question here is just a rectangular window since we simply select our samples. And it gives us an estimator with a variance which is proportional to the square of the power spectral density. There is a slightly more accurate formula for the variance which is given by this expression, but the second term here in the bracket will tend to 0 for all frequencies except the 0 frequency when n tends to infinity. So for sufficiently large n, this is a reasonable approximation of the variance. So what we know about the periodogram is that since we're convolving with a fairly long window, with a length n window, we get a good spectral resolution, but the variance here being proportional to the power spectrum squared is very bad. The periodogram also had a second property in that since we are using a rectangular window, simply just picking our samples, we get a fairly large spectral leakage. That spectral leakage can be addressed by the modified periodogram, where we explicitly apply a different window than the rectangular window, giving us the modified periodogram, where the estimate is given by the data multiplied by a window, but otherwise processed according to the periodogram, also taking the window's power into account in order to get a properly normalized power spectral estimate. The bias of that one is given in the same way as the periodogram by the true power spectral density convolved with a particular window that we've chosen for the modified periodogram. However, choosing or moving from the periodogram to the modified periodogram doesn't address the variance, while it does address the spectral leakage by reducing the side lobes. In order to reduce the variance of the power spectrum estimate, we can apply one of several methods, including Bartlett, Welch, and Blackman-Tukey's method. So Bartlett method works by averaging periodograms obtained by shorter windows. So that leads to two effects. So the bias is changed by the fact that we're changing the length of the sequences or the window length. So generally this quantity here will become wider and we get poorer spectral resolution. And what we gain instead is that we get a reduction in the variance. So if we average over k blocks, we get a variance which is 1 over k times the variance of the power spectrum estimate. And this leads to a better variance, as noted, at the expense of poorer spectral resolution because we're using shorter windows. One can improve upon this by allowing the windows to overlap and also applying a more clever window than the rectangular window. And that led us to Welch method, where Welch method is similarly an averaging of modified periodograms, in this case where we're using a particular window function. And the bias of that method is given in the same way. So the resolution is determined by the size of the window, or the particular window that we use, also with its length. Right? And we have this normalization for the power here, obtained from the window and the length of the sequence. When one can show, and this was shown in Welch's initial paper on the Welch estimator, that the variance of this estimate is given by 9 over 8 times the number of blocks that we have, assuming a triangular window and 50% overlap. And if one looks at this 9 over 8, it seems like the variance is larger than the one for Bartlett's method. But the thing to remember here is that using Welch method allowing for overlap allows us to have more blocks than what we could in Bartlett's method. So we can have almost approximately 2 times as many blocks if we have 50% overlap. So the variance in comparison to Welch method is actually 9 over 16 times the periodogram estimate, or we get close to 1/2 improvement in the variance for Welch method. Rather than averaging the periodogram or the modified periodogram as we do in Bartlett's and Welch method, we could also achieve a better power spectrum estimator by simply averaging in the frequency domain or multiplying the autocorrelation function with a shorter window function. And this led to Blackman-Tukey's method. So the Blackman-Tukey estimate is given by the Fourier transform of the autocorrelation estimate multiplied by this window. And if we understand the basic properties of Blackman-Tukey, it's easy to derive the bias. So the bias here is given as the expected value of the estimator being the true power spectral density as convolved with the Fourier transform of the chosen window. So one thing to look out for when one considers the spectral resolution of this method is that we get the window as the direct Fourier transform of this window function in this expression, and not its absolute value squared. And that will have some effect on the level of the side lobes and also the width of the main peak, since we're considering the direct quantity here and not its absolute value squared. In terms of variance, one could also derive an estimate or an expression for the variance of Blackman-Tukey's method, and it's given by this expression, which is not as clean as the 1/k expression that we had for Bartlett's method or the 9/8k as we had for Welch method. But generally speaking, this sum here over the window will evaluate to something which is less than n, meaning that we get a reduction in the variance as compared to the periodogram estimate. So in order to understand this multiplicative factor in the variance, let's consider again the bias term, which was given by the true power spectrum of the process convolved with the window's Fourier transform. So if we want the expected value here to be asymptotically unbiased, or not to change the absolute power of the true power spectrum when we do this convolution, one property that we need to satisfy is that the integral over the window should evaluate to 1. So this is essentially saying that we do proper averaging so that we don't also introduce a scaling. So this has a number of implications in terms of the window function. So do you think that this integral expression here, that saying that the window in the Fourier domain must integrate to 1, implies that all taps of the window in the time domain are strictly positive, that the center tap is equal to 1, that the sum of the taps in the time domain sum to 1, or that the sum of the square taps sum to 1? Well, the right answer is option number 2. So the center tap of the window should be equal to 1. So if you look at this expression, one can interpret this as the inverse Fourier transform evaluated at k equal to 0. So typically in the inverse Fourier transform we would have an exponential function here being e to the power of j 2 pi nu k, where k is equal to 0, that evaluates to 1, and it reduces to this expression, which gives us number 2 as the correct option for the window. So all of these mathematical expressions for the performance of these different estimators allows us to, in a rigorous fashion, quantify the things that we see in the graphics when we do the spectrum estimator. So here again, considering the AR4 spectrum that we looked at many times before, we saw that the periodogram gave a very noisy or a very high variance estimate of the true power spectral density, but with a good resolution. Applying Bartlett's method, we saw that we got a decrease in the spectral resolution with the benefit that we get a reduced variance. So what you see here towards the edges, this one and this one, is not really variance of the estimator, rather it's spectral leakage from the peaks. And we could address the spectral leakage by applying Welch method, where we apply the window to the different blocks, pushing down the amount of spectral leakage and getting something which is closer to the true power spectral density. So in this case we see an estimate for 1,024 samples with blocks of length 64 and the number of blocks equal to 31, so we have 50% overlap in this particular example. And we also see that by applying Blackman-Tukey's method, we could get a very similar estimate by different methods where we did the averaging in the spectral domain. Another thing that the mathematical expressions now allow us to do is to objectively compare the different estimators with each other. So one can do this in terms of several different metrics. So one metric is of course the variance of the estimator. Now the variance of the estimator, as we've seen, depends on the true power spectrum. So in order to remove that effect, in order to not have to consider which particular spectrum we're estimating when we look at the variance, it's very common to take the variance of the estimator and divide it by the expected value squared. And as we've seen that all of the variances are proportional to this, this gives us a quantity which is not affected by the absolute scaling of the power spectrum, and this quantity is sometimes called the variability of the spectrum estimator. So if we do this for the periodogram to begin with, we saw that the variance of the periodogram was just the expected value of the power spectrum, or the true power spectrum, which asymptotically for large n approaches the power spectrum squared. So taking the variance and dividing by the expected value squared gives us something divided by itself, so equal to 1. So the variability of the periodogram is simply equal to 1 by the previous expressions that we have. Now, looking at the other estimators which trade off resolution for variance, we have to take into account the particular resolution of the estimator. Since the different estimators for different windows give different resolution, the only fair way to compare them is to set the parameters so that the resolution are the same in all cases, and this gives us an objective or a fair comparison between the different methods. So one can compute the variability for Bartlett's method using the previous expressions and show that this is equal to 0.89 divided by the number of samples and the spectral resolution required, assuming a large number of samples. Doing the same thing for Welch method gives us a variability of 0.72 divided by the number of samples for a particular resolution in the spectrum. So we can see an explicit expression here making precise the claim that Welch method is preferable over Bartlett's method, since the variability for the same resolution is lower than the one for Bartlett's method. So I previously said that you can get the variance of Welch at about 50% of the variance of Bartlett's method with 50% overlap. And the reason why this number here, 0.72, is not half of 0.89 is simply because in Welch method we also apply a window which reduces the spectral resolution somewhat. And in order to account for that, we need to take slightly larger blocks in order to get the same spectral resolution. And when we account for that, the actual gain is this drop from 0.89 to 0.72. And this whole calculation is again built on the assumption of a triangular window with 50% overlap. And it also allows us to compare Blackman-Tukey's method with the previous methods, which were based on averaging of the periodogram and the modified periodogram. And in this case we get a variability of 0.43 divided by the number of samples and the required spectral resolution, assuming that we apply a triangular window in Blackman-Tukey's method. So here again we can objectively say that Blackman-Tukey in terms of the variability is better than both Welch and Bartlett's method. Let's now consider a question based on this. So suppose that we're using Bartlett's method, which had the variability given by this expression which we saw on the previous slide. If we want the resolution of Bartlett's method, meaning the 3 decibel bandwidth of Bartlett's method, to be as good as for the periodogram, what will then the variability of Bartlett's method be? Will it be 0.89? Will it be equal to 1? Will it be equal to 0.89 divided by the number of samples? Or will it simply be 1 over the number of samples? Well, the correct answer is option number 2. And there are several ways to see this. One way is simply to use the formulas. So we know that the resolution of Bartlett's method is 0.89 divided by n. This was covered in a previous video. And we have the expression for the variability of Bartlett's method. So simply taking this expression for the spectral resolution of the method and plugging it into the formula for the variability will give us a variability of equal to 1. There is another more intuitive way of arguing this though. If we want Bartlett's method to have the same resolution as the periodogram, the length of the window needs to be the same as for the periodogram. And the periodogram used all of the data in a single block, and in order to have the same length in Bartlett's method we can only allow for one block. So under this constraint, or under this assumption that we make in the question, the Bartlett's method is actually equivalent to the periodogram. It's the same thing, which should give us the same variability, and the variability of the periodogram was equal to 1. So let's summarize. We've seen that the spectrum estimators can be characterized in terms of their bias, which implies their spectral resolution, or by their variance. Comparing the different estimators at the same resolution and ranking them according to the variance that they provide, the ranking is as follows. So Blackman-Tukey is the one with the best variance for a given resolution. After that comes Welch, and finally Bartlett's method. So choosing between Welch and Bartlett, one should always choose Welch if one can have access to the whole set of data. When the data comes in as block, there could be reason to choose Bartlett's over Welch. Choosing between Welch and Blackman-Tukey, if one can compute an estimate of the autocorrelation, it's better to use Blackman-Tukey, at least if one are using triangular windows, because the Blackman-Tukey method has lower variability than Welch for the same spectral resolution. However, there are other aspects when choosing spectrum estimators, so one shouldn't blindly go by this ranking in choosing them. So one has to understand the full set of properties for a given estimator when making an intelligent choice which one to use.